Yeah. So good afternoon and welcome to this afternoon session. That is session number 2 of this webinar, which is on the theme of advanced base isolation system in real life projects in India. I am Alok Bhaumik and I am the president of Indian Association of Structural Engineers. Uh, some of you might have attended the morning session, which was the first session, very successfully conducted in the morning, and which was on the topic of fiber reinforced elastomeric isolation system, an indigenous invention for safer future. And there, where we talked about the base isolation, which is with fiber elastomeric system. The second session, which is now, which will be on the topic of new generation sliding base isolation system for improved seismic performance of structures. And this will be, our speakers are Professor R.S. Jangid and Professor Vasant Matsagar of IIT Delhi and Professor Jangid of IIT Bombay. And both the speakers have done pioneering research in the subject of base isolation. And this session will be moderated by Mr. Vipul Ahuja, Vice President of Indian Association of Structural Engineers and a well-known expert in the field as a structural consultant working in the area of base isolation of buildings. Uh, I, I sincerely thank both the speakers and the moderator for participating today and for sharing their knowledge and experience with us. Friends, this and base isolation is a new trend in earthquake engineering, where the structural response is decoupled from the ground motion, and this is a leapfrog jump in terms of seismic safety. There are many structures which should be operational post major earthquake so that the post disaster management operations can be successfully conducted. Examples like hospitals, like school buildings, like administrative buildings, all these buildings have to be operational right after the earthquake, and therefore such buildings definitely require a system of base isolation where not only the structure per se but also the non-structural elements remains intact after any major earthquake. So the first session, as I mentioned, was to deal with base isolation with elastomering bearings, fiber reinforced. And this session, we will talk about the sliding elements in the base isolation system. The webinar is being organized jointly by IES Structi and ISET, two professional associations which are dealing with, the earthquake engineering. Let me give you a little bit brief about these two associations before I hand over to Mr. Vipul Ahuja for moderating. ISET, it provides the forum for scientists and engineers to come together and exchange ideas on the problems of earthquake technology. The association also helps to disseminate knowledge on seismological and engineering aspects, and it promotes the research and development work in the field of earthquake engineering and technology. The IAS Structi, the Indian Association of Structural Engineers, is the national apex body of structural engineers in India. It was established in 2002 by Mr. Mahendra Raj, the legend, and this was done with the objective to cater to the overall professional needs of structural engineers. The association promotes the interest of structural engineering in the country and works towards enhancing their status in civil society. The association aids skill development through various training programs, CPD, webinars of this type, and that is what the associations, the as IAS Structure does. It is now time for me to hand over the floor to Mr. Vipul Ahuja to conduct this event. But before I do that, it is my great honor and privilege to introduce Vipul, who is a very good friend of mine and is the Vice President of Indian Association of Structural Engineers. Mr. Vipul Ahuja has vast experience of more than 40 years in the field of structural and earthquake engineering. He has designed experience of using steel, concrete, reinforced masonry, fiberglass, and timber for building material. He has experience in engineering of performance based design, base isolation, and damper applications in high rise buildings, which is steel, concrete, or composite. He has also designed a base isolated commercial building and another high rise 36 storied building, even up to, good for construction stage, which is yet to be built. And he has performed several studies, including the double isolation system, viscous dampers, tuned mass dampers. He has designed hundreds of buildings of residential, commercial, and retail spaces, hospitals, bridges, shell roofs, long span pre-stressed concrete structures. He was in US for 14 years, and during that period, he worked with many prestigious firms like Skidmore, Owings, and Merrill. And after that, in India, he has worked for about 26 years. He leads his own firm to date. His USA experience in California includes engineering of non structural components in hospitals and nuclear power plants to stiff Californian standards. He has experience of using current Indian and international codes like USA, Australian, Japanese, and European standards, and has several technical papers to his credit. So I now hand over the floor to Vipul for conducting this event. Thank you.
Uh, Thank you very much, Alok, for your kind words. I would, I'm very pleased to open this afternoon session. And our first speaker is going to be Professor Jangid. So before I hand over the stage to Professor Jangid, I would like to give a little brief introduction about him. So, Dr. Jangid is a professor in the Department of Civil Engineering at IIT Bombay. He received his BE honors in civil engineering from University of Jodhpur in 1989. Subsequently, he did his MTech and PhD in structural engineering from IIT Delhi in the year 1991 and 1993, respectively. His research interest includes the aseismic design of structures by active and passive control devices and dynamic analysis in non-classically damped systems. His recent research contribution includes the base isolation of near fault motion and its application to bridges and tanks, multiple tuned mass dampers for vibration control and active control of torsionally coupled structures. He received Young Engineer Award of Indian National Academy of Engineering in 1998 for significant contribution towards research in the area of earthquake engineering. He also visited the University of California, Berkeley for 6 months in 1999 and carried out research in area of earthquake engineering at Pacific Earthquake Engineering Research Center under the Boy Cast Fellowship scheme at the Department of Science and Technology, New Delhi. He also received the IIT Bombay Paper Award for year 2014. He worked as a seismic consultant for the government of Maharashtra in repair and retrofit of houses affected by Latur after a Latur earthquake in 1993. He also carried out research for BARC for earthquake resistant design of nuclear structures and its components using passive control devices. He had published several papers in the international journals, about 170, and conferences, and co-authored a book on structural analysis. He guided several doctoral, like 28 numbers, and master's 60 theses in structural engineering. In IIT Bombay, he also served as Associate Dean, IPS, served as Independent Director for ETC Network Limited Company of the SL Group. Currently, he is a member of the High Rise Committee for Structural Safety of the Tall Buildings in Mumbai. served as a consultant in many prestigious buildings, infrastructure projects, and historical structures, including Grand Pagoda at SL World, Gurai. So let's give Professor Jangir the big welcome, and please I now hand over the charge to Professor Jangir for his presentation. Thank you.
Uh, Good afternoon, everyone. Thanks, Vipul, for your nice introduction. And first of all, let me thank Indian Association of Structural Engineers, as well as ISET, to give me opportunity to present some of my research, which I did at IIT Bombay in the area of base isolation. So let me share the screen.
The one little added note is please reserve your questions for the. We'll take up the Q&A at the end of all the questions in the Q&A box in the chat. Thank you.
Are you able to see my screen? No.
Yes, we will.
Is it visible now?
Yes, yes.
Okay. Okay. So I'll be presenting some experimental studies which were carried out on a prototype small scale models of the isolation system and their implementation in the components, not in a full-fledged structure, but a components of the structure uh, in nuclear structures. So, two types of base isolation systems, namely the laminated rubber bearing and sliding bearings, they were designed and fabricated at our institute through a sponsored project by BRNS. The various experimental tests we were performed on these bearings for the evaluation of their static and dynamic properties, and based on these small scale models and properties. The small scale steel frame models were developed and tested with a condition of isolated and without isolation. The excitation that was considered for stack table was harmonic as well as some simulated earthquake motion, and experimental results were then validated through mathematical models, and it was observed that there is a good comparison between experimental and analytical results. Finally, these isolation systems which were developed, though were very small in size, were implemented in a UPS system for the nuclear structures. So this is a typical view of a isolation system, and we call it as a laminated rubber bearings, which consist of the alternate layers of the steel plate and the rubber. Rubber provides the horizontal flexibility to the system, and because of this, the period of the structure on which they are resting gets elongated. Now, the purpose of the steel plate here is, as as mentioned by Professor Dev in the morning, that to increase the vertical stiffness of the isolation system. In the morning, in place of these steel plates, carbon fiber, polymers were used, and because of using the carbon fiber polymers, the bearings were lighter, and apart from this, they have more capability to dissipate energy, or they were having more damping in the system. So details of the FR fiber reinforced elastomeric isolators were presented by both Professor Dev as well as Professor Datta, and in which they replaced these steel plates with the carbon fiber. So this is a typical cross section, and depending upon the layers and the steel plate, one can find out what is the horizontal and vertical stiffness of the isolation system. The horizontal stiffness does not depend how many steel plates are provided, but the vertical stiffness depends the number of steel plates provided, because it changes the EC. And because of the change in the EC, the vertical stiffness changes. For example, if you increase the spacing, uh, uh, of the steel plate by 2 times, then stiffness reduces by 4 times. What it means that by decreasing the spacing by half, I'm increasing the stiffness by 4 times. So depending upon the requirement of the vertical stiffness, I can adjust the uh, spacing of these steel plates. Now, as I told you that we carried out some tests, and on the left hand side of this slide, horizontal, load deformation, uh, you know, experiment for horizontal load deformation behavior is shown, where two isolators were kept one above the another, and it was pushed. And with the help of the cell and other devices, the displacement and the force were measured. On the right hand side picture, you can see the testing of the isolation system in the vertical direction. This was the force deformation behavior in the lateral direction, and one can see that it's almost a linear behavior in the horizontal direction. Now, once we develop these small scale isolation system, then steel frame models were developed, 1-story and 2-story frame models. And there were two types of laminated rubber bearings were there, LRP1 and LRP2. These models, then we put it on the shake table test and seen the performance of the models in terms of the reduction in the acceleration with and without isolation conditions. So this is the shake table which we have at our institute, though it's not a very big shake table. It's just a 5-ton capacity shake table. So very limited or a very small scale model we can test here. So you can see that this is a 2-story frame model resting on the isolation system, and then these are the gauges which are provided to measure the acceleration and displacements at various levels. And this is the another one, which is the same one but fixed one. So the difference between top and bottom is that the top one is the isolated model, and the bottom one is the non-isolated model. On the right hand side, one can see the analytical and experimental response, and one can see that there is a good comparison in the analytical and experimental response under harmonic excitation. This is the model when it was subjected to the simulated earthquake ground motion, and this is the displacement time history of the earthquake ground motion that was used, which we call it as the input motion, and this is the output motion. And one can see that there was a substantial reduction in the acceleration of this structure. This slide shows that when the bearing was tested for the ultimate load, then it underwent a deflection of 45 mm and a horizontal load of 386 kilogram. This slide shows the acceleration of a isolated and non-isolated model, and one can see that there's a substantial reduction when isolation system is used. The bottom graph shows about the displacement in the isolation system, and for the two model, which were one story and two story frame model, they are having more or less same displacement because in an isolated structure, normally the response does not depend upon the number of story, but it depends what is the total weight of your structure. Another type of bearings which we tested initially, which was almost maybe 10 to 12 years back, uh, this is just a simple sliding bearing, and one can see here these are the four PTFE, squares and or four PTFE portions, and then there's a steel plate is there at the bottom, and this isolation system is made through sliding of this PTFE bearing, PTFE on the steel plates. This is the simplest, sliding isolation system. The advanced isolation system includes like a friction pendulum system or a resilient friction-based isolation system. However, there are furthermore advanced sliding isolation system has also, studied and developed. Professor Matsagar will be talking about the details of the advanced sliding isolation system, which has been developed and studied at IIT Delhi. So on the right hand side, one can see here to find out the friction coefficient between PTFE and the steel plates. So simple experiment that has been done. So this is a model of a structure, one story structure with sliding isolation system, and it's just a one can call it as a pure friction sliding system, as there is no resisting, there is no restoring force in it, and because of this, what happens is that it undergoes a large drift at the end of an earthquake. So we don't want that after an event of the earthquake, the structure which is resting on a sliding isolation system undergoes a permanent, permanent displacement or a permanent residual displacement, after which it has shifted from original position to, let's say, uh, uh, 10 centimeter or a 20 centimeter like that. And therefore, what we normally do is that in the form of some way or a other, some restoring force is provided. In case of a friction pendulum system, this restoring force is provided through the gravity action through the curved surface. And once it moves along that curved surface, the structure has a tendency to come back towards its original position, and which we call it as a restoring portion. These are the shake table test one can see here. This is the model which is with no isolation system. This is a model with sliding isolation system, but no restoring force. And this is a model in which there is a sliding isolation system along with the restoring force, and restoring force is provided with the help of these cantilever rods. And it was observed that a sliding system with a restoring force performs better than the pure sliding system. On the right hand side, under the harmonic excitation, there is a comparison between experimental and analytical results, and one can see that there is a good match between the two. This slide shows the variation of the acceleration, top floor acceleration, and the isolator displacement. And one can see that due to isolation system, there is a substantial reduction in the acceleration of the structure. However, on the left-hand side, this is a system when there is no restoring force, but on the right-hand side system, there is a restoring force and there is almost zero residual displacement. So what it means that the structure is at the same position after the event of the earthquake. Now, apart from the two isolation system, laminated rubber bearings and the sliding isolation system, we also developed a small scale model of a lead rubber bearing in which in the same bearing a hole of 12 high was developed was made, and in that hole the lead was inserted. So this is the lead core that is the inserted in the bearing. This is the actual photograph of the bearing where it's a lead rubber bearing. The purpose of the lead in case of a isolation system is to provide the initial rigidity to the system so that the system is almost under static condition or a no vibrations during an event of a strong wind or a minor earthquakes. However, when major earthquake comes, then the yielding in the lead takes place, and because of this yielding, the additional hysteretic energy is developed in the system. So that's the advantage of the lead core. This slide shows the host deformation behavior. There were four type of isolators were there, and this is behavior in the vertical direction. The bottom side is in compression and top side is in tension. This slide shows the host deformation behavior of the lead rubber bearing in the horizontal direction, and one can see that it is a hysteretic in the nature, and this hysteresis is coming because of the presence of the lead in the bearing. And because of this hysteretic behavior, the additional hysteretic damping in the system is added, which dissipates the seismic energy. This is a simple way to model a lead rubber bearing using the Vance equation. This is the restoring force, and this is the value of this parameter Z can be obtained by solving this first order differential equation. There are several parameters like beta, tau, A, and N, and by appropriately selecting the values of these parameters, one can model the various types of bilinear behaviors. This slide shows the experimental and analytical post deformation behavior of the lead rubber bearing, and one can see that there is a slightly good match between two. Then the lead rubber bearings, they were tested on the small scale models, and the response were obtained both experimentally as well as analytically. This is the model of one-story building model on lead rubber bearing under harmonic excitation. And again, on the right-hand side, experimental and analytical response is shown. This is the response of a two-story building model. And again, one can see that there's a good comparison between experimental and analytical response. This is the ultimate, the test of the bearing under ultimate load condition, and this bearing underwent a maximum deflection of 30 mm and took a horizontal load of 430 kilograms. Now, the purpose of this test was to, use these bearings on a not the nuclear structure, but some components in the nuclear structures. And what it were used were to isolate the UPS. UPS is an important, accessory in a nuclear structure where power should, continuously should be supplied to the nuclear structures. This UPS system was designed uh, using isolation systems, and what was done in this one is there were 6 bearings that were used in this one. Uh, for example, uh, 2 laminated rubber bearings, which you can see on this side, and 2 on the front side. So total 4 laminated rubber bearings were used. And in the middle, a sliding bearing was used. And the purpose of this sliding bearing was to take primarily the majority of the vertical load of this one, and the load transferred to these bearings was tried to reduce it amount. And because of this, one can ensure the stability of the isolation system. The time period which was kept uh, for this structure was 2 seconds, as mentioned by Professor Dev in the morning. That 2 seconds is a typical time period of the structure where one can achieve the isolation system. So 2 seconds was the time period. 10% damping was considered, and this system was observed to be till date working nicely. As such, there is no deterioration, etc., has occurred in the isolation system. So this is the last slide, which I will summarize, and after that, Professor Matsagar will take over and will talk in detail about the sliding isolation system. So what I just summarize that 3 types of isolation system, namely the laminated rubber bearing, lead rubber bearing, and sliding isolation systems were developed. And the using we use whatever state of the art knowledge at that time it was available to us. So this was 10 to 12 years back. The effectiveness of isolation system is demonstrated, and the base isolation for typical nuclear structure equipment and panels can be designed and fabricated. There was good agreement between analytical post-deformation behaviors of various isolation systems and the accidental one. And one can use the analytical model to get the response of the actual models. Based on this knowledge, we implemented this seismic isolation system in a UPS system. So thank you very much. Uh, I
So,
try to take slightly less time so that Professor Matsagar will get more time, will present more real examples of the isolated structure.
we have just a couple of questions. I just thought normally I would have just kept it at the end, but for you, we have one anonymous person asking what is the maximum load capacity of the shake table?
This was a 5-ton one, as I told you in my presentation.
Then there's one which says, can you explain how the vertical load on isolator was given during the laboratory test?
It's just like a compression test which we perform in case of like a cubes and that thing. So same way it was tested in compression.
Okay. So I think these are all the questions I have for you from on the chat. There's one, of course, for the association. They want people from Kashmir. They want this on a YouTube link or something that will help them.
Sure, sure, sure.
Okay. So thank you very much, Professor Jangid. And now we are going to move on to Professor Matsagar's presentation, I would like to first, give you a little introduction for Professor Matsagar. So, for the benefit of those who did not attend the morning session, for those who had, of course, it will be a little repetition, but please bear with me. So, Professor Matsagar is currently serving as Professor and Dogra Chair in the Structural Engineering Department of Civil Engineering in IIT Delhi. And he obtained his doctorate PhD from IIT Bombay in 2005 in the area of earthquake engineering for his PhD thesis titled Earthquake Behavior and Impact Response Control of Base Isolated Buildings under the supervision of Professor Jangid, from which they have been honored with the IIT Bombay Research Paper Award. um, and in 2014, his patent titled Base Isolation Device for Earthquake Resistant Structures has been awarded with another patent titled Tunable Shock Absorbing Passive Control Device for Vibration Control and for Vibration and Shock Response Control of Structures, has been filed in 2019. Also, he has filed copyright for a method of semi-active vibration control of structures in 2020. So Professor Masagar is the recipient of numerous national and international recognition, including Humboldt Research Fellowship for Experienced Researchers, Erasmus Mundus Awards, DST and DAE Young Scientist Award, DAAD Research Ambassador and DAAD Awards, IBC Award for Excellence in Built Environment, Institution of Engineers, Young Engineers Award, IIT Delhi, Teaching Excellence Award, etc. Professor Matsagar has served as member of National Building Code NBC 2016 of India and is currently serving as a code development committee in Bureau of Indian Standards, Indian Research Road Congress, and International Standard Organization ISO. In the BIS, he is currently serving as member of the Earthquake Engineering Section Committee of CED 39 for Indian Standard Code 1893. In ISO, he is currently serving as a group member, working group member on seismically isolated structures. Currently, Professor Matsagar is serving as the editor-in-chief of the Indian Society of Earthquake Technology Journal and convener of the Structural Dynamic Forum of ISCT. He is an editorial board member of the Bulletin of New Zealand Society of Earthquake Engineering, that is BNZ as SEE. Proceedings of the Institute of Civil Engineering, ICE, Structures and Buildings, Advances in Civil Engineering, Indian Concrete Journal, and few others. He is a guest editor of journals, namely Institution of Engineers India, Series A, Shock and Vibration Control Frontiers in Built Environment, Journal of Low Frequency Noise, Vibration and Reactive Control, and served as responsible editor for the Earthquake Spectra Journal. Professor Matsagar has been involved in the design of 5 real-life base isolation projects in India, 3 out of which are completed and nearing completion, 2 are under construction. Today, he will talk about one among the base isolated buildings and his presentation titled New Generation Sliding Base Isolation System and Improved Seismic Performance of Structures. So let's welcome Professor Matsagar and over to him. Thank you. Please go ahead. You are probably muted, Professor Matsagar. We can't hear you. Yeah. You were muted, Professor Matsagar. Now I think you're unmuted now. Go ahead, please.
Okay, thank you, Ahuja Saab. Am I audible now?
Yes.
Is my screen visible, sir?
Yes, it is.
Okay. Thank you for your kind introduction, Mr. Ahuja, and good afternoon, one and all, once again. It is rather difficult to speak after four giants in base isolation technology have spoke, and that too towards the end of the day, but I will try my best. So the very theme of this particular seminar being organized by the Indian Association of Structural Engineers in association with Indian Society for Earthquake Technology was to give some glimpse of real life projects built with the base isolation technology, as well as particularly by using the advanced base isolation system rather than the conventional base isolation system. So in my presentation, I had decided to keep focus exactly on these aspects, that the presentation will focus on the real life project only, and it will have the base isolation system, which is non-conventional. So with this, I would start my discussion on these new generation sliding base isolation systems for improved seismic performance of structures. This will be my outline of the presentation. I will cursorily talk about the structural vibration control because Professor Dev has already introduced the structural vibration control as well as the base isolation technology in general. I will move on towards the base isolators, which are also called anti-seismic devices in other parts of the world. And then I will talk about the base isolation system, which has been used in this real life project in India, which is either called double curvature or called double concave friction pendulum system. It is also abbreviated as DCFP system or DCFPS. Now, though I do have some mathematical equations of the functioning and deriving those mathematical equations for a multi-degree of freedom system when base isolated by using the double curvature concave friction pendulum system, today I decided that I will focus more on the real life aspects and from the structural design viewpoint, how these systems are modeled in the software and how the results can be used for designing some real life project. So for researchers, it might be a disappointing note that I may not be presenting some differential equations and their solutions today. But for practicing engineers, they will be able to build a confidence that it is very easy to adopt this kind of system in terms of their modeling and design in whatever conventional earthquake resistance design that we have been doing. And then I will turn my focus towards the real life building that I'm involved with and conclude my presentation then on. So very quickly, in the Indian terms, we categorize base isolation into a passive response control system, which is a vibration response control system. Though in Japan, they categorize base isolation system separately than the vibration control system. But in India, we put them together. It is not also out of the place to say that even the kind of isolation systems that we use, they are combinations of different isolation systems. Just during the previous presentation of Professor Jangid, one of the participant has asked, can we use different types of isolation systems? So the answer is yes, we do use in fact different kinds of isolation system in order to make it cost effective. So we use some systems which are costly in a limited number and rest of the systems are in abundance so that we have complete isolation. So if we use different kinds of such devices which are in terms of their functioning different from one another, then that is called the hybrid isolation system. So my focus today will still be on the base isolation system in general and particularly on the sliding isolation system. Again, Professor Dev in the morning session has explained the functioning of the base isolation system, how it is different from the conventional earthquake resistant design philosophy. So one of the prominent feature of base isolation system, as he has mentioned, is avoiding the frequency of the structure matching with the external excitation frequency, that is the major excitation frequency coming from the earthquake. So thereby there is no resonance and there is no excitation causing amplification in the response. In addition to that, the another advantage of using base isolation is the change in the fundamental mode shape. So instead of the cantilever mode shape, the first mode, in base isolation, it changes to the isolation mode corresponding to the fundamental frequency or in the natural time period, and thereby the superstructure remains almost rigid. There are hardly any deformations in the superstructure in the first isolation mode. So those deformations, of course, are attributed to the flexibility of the isolation system. And we know that flexible structures, they perform well during the earthquake than the steep structures. So in terms of dynamics, of course, the time period is lengthened, frequency is reduced when we incorporate such flexible isolation systems. And this helps in making the structure more flexible than the conventional structure. And the higher modes contributing towards the response, they reduce. Plus, these isolation systems have additional means of dissipation of energy, either in terms of the viscous damping or in terms of the friction. So today, again, I will focus more on the energy dissipation through the friction mechanism. However, again, it was being discussed by my predecessor speakers that the isolation system also need to provide some initial rigidity so that during the minor earthquakes or during the ambient winds, the systems does not start oscillating and causing discomfort to the users. So we can otherwise make the system quite flexible. So during the earthquake, it will perform quite satisfactorily. However, during the service condition, it might cause discomfort to the users. So essentially, we have to strike a balance between these two, how stiff and how flexible. So that is the deciding criteria while designing the isolation systems. So in addition to that, restoring capability, as was being discussed in the morning session, is another important feature in the design of isolation system. And the last advantage of using base isolation system is they can be easily monitored closely all the time, and they can be replaced whenever so required very, very conveniently without disrupting the ongoing functioning of the structure where it is. So theoretically, as all of us are familiar with base isolation technology and the sequence of the construction, that we have a foundation, on top of that we have isolation systems, and then a base draft, and top of that we built a structure. And so that during the excitation, most of the deformations are concentrated only at the isolation level, and the superstructure remains more or less intact, or it behaves rigidly mostly. The lower modes are eliminated from the superstructure. So thereby the base shear in the columns or the lateral load resisting elements reduces down quite substantially. So all this theoretical background is known to us. What I'm going to present today is how it is realized in the real life projects. So flow of my slides will be exactly in the same manner as to after the isolation systems were designed for a structure in the design office, what kind of construction steps were adopted at the site in order to have this base isolation structure constructed in Noida here in Delhi. So on the part of design of the isolation system, I'm giving some background. Again, I will not repeat the part which Professor Deb has already mentioned. But one takeout message from this period shifting is it is the designer, structural designer, who decides as to what should be the time period shifting in the structure. So it also answers yet another question asked by one of today's participant, that can we use it for high-rise buildings or tall or flexible structure? So essentially, when we talk about a structure, it's the fundamental frequency. If it is in the time period zone where it attracts significant amount of spectral acceleration and corresponding to that the seismic base shear, our intention is to shift this time period to that zone of the time periods where it will attract lesser spectral accelerations and corresponding base shears. So if I consider the example of a flexible or tall structure, its time period will be already in the zone where it will attract lesser seismic forces. So therefore, isolation may not be necessary. Still in this discussion, I did not mention what time periods. I'll just give my information from Japan, where they are also using base isolation for a structure having time period in the range of 3 seconds. So they are even shifting this 3 seconds time period to a much larger time period so that the effectiveness of isolation can still be achieved. Nevertheless, in our context, if we talk about 5 to 10 stories of building, approximately it will have a time period of about 0.5 seconds to 1 second. And our objective would be to elongate that time period or to lengthen that time period to maybe about 3 seconds plus minus, depending on what is the choice of the designer. So corresponding to those large displacement that are associated with the elongated time period, we need to also have designed the damping so that the displacements are controlled without affecting the seismic forces. So it is the decision of the designer as to how the time period elongation is to be obtained. So typically, as a ballpark figure, if we are increasing the time period beyond 3 times, means we increase the time period up to about 3 or more, then we do achieve economy and exploit all the advantages of base isolation system. And in terms of damping, what is the tune or magnitude of damping that we are talking about? So typically, steel structures exhibit damping of around 2% of the critical, whereas reinforced concrete structures exhibit damping of around 4 to 5, depending on how extensively it is cracked. So if it is more cracked, then the damping experienced is in the range of about 5% of the critical. Whereas in terms of the damping of the isolation system, we are talking about damping in the range of 10% or more, particularly when it comes to the elastomeric bearings. So there are different types of isolation devices, and these are very, very representative isolation systems which are presented on the slide. There are large number of such variants and different types of isolation system. In particular, rolling isolation systems are not shown here. So some of the rolling isolation systems also we have been able to implement in the industry as shown by Professor Jangid for equipment isolation or for machine mitigating the machine vibrations. However, in today's presentation, I will focus more on the friction pendulum type of isolation system, which have been used in a real life project in India. So Professor Dev and Professor Anjan Datta today morning talked mainly about first the elastomeric isolation system and later on about the fiber reinforced elastomeric bearings used in the real life structure in Arunachal Pradesh. Before development of the isolation systems which are based on the sliding friction, these kind of bearings based on the elastomer and some lid plug were quite popular. But nowadays, even sliding isolation systems are being considered for real life projects. Again, the development of the friction isolation system is not all of a sudden. Initially, only sliding isolation system without restoring forces were proposed. And then some external means was applied in order to develop the restoring capability. So there had been a combination of the friction isolation system and the slide based on the sliding friction and the elastomeric bearing, where the elastomeric bearing mainly takes care of the restoring and some damping, whereas the sliding isolation system provides the means of energy dissipation. However, in purely sliding system, in order to give the restoring capability, a very novel idea has been thought of. Can we use a sliding surface which is concave or curved in nature? So the amount of curvature that we give will decide as to how much restoring capability we achieve. For example, if the curvature is larger, it means radius of curvature is smaller, then it will have higher restoring capability. However, it is at the cost of compromising with the effectiveness of isolation, because it will be almost close to a fixed base building, so responses will be higher during the seismic event. On the other hand, if we make the curvature larger, if we make it more and more flatter, so thereby the restoring capability is reduced to some extent, but it will improve the isolation capability. It will be able to help us reduce down the effect of seismic forces on the lateral load resisting element. So again, it is the designer who would decide what should be the curvature of this pendulum system. Now that curvature will decide as to what is the frequency or time period of the structure which is being designed in this case, particularly in the first mode. So this is comparable with as if having no connection with the ground, which is shaking, and thereby we will be able to protect the structure. But of course, this is impractical. We cannot have, let us say, some hydrogen balloons connected to the structure, which can lift the structure up so that the catastrophic ground motions do not cause any harm to the structure. So instead of using these kind of hydrogen balloons which can lift the structure, we interpose a layer, and that layer, in this case, we are talking about a conventional friction pendulum system, which has a single curvature here. So it consists of this kind of an articulated slider, and on top of which moves on top of the bottom slider here, and the curvature of this will give you what is the time period that we can achieve. So this is comparable to a single pendulum having particular length, and when it oscillates, it has a certain time period, and the building which is on top of this will be able to achieve that kind of a time period. So this is the construction, how the conventional friction pendulum system would look like. Again, there have been some apprehensions as to what will happen, for example, when this slider oscillates in few cycles. In the initial cycles, the friction might be in the range of, let us say, 5%, but later on the friction may reduce because of the wear and tear of these two sliding surfaces against each other. So there have been some research put into and check as to how the sliding systems, what happens to the friction between these two sliding surfaces over number of cycles. So that depends on what kind of material is put in between, and these days some advanced materials are available which are able to maintain the friction coefficient as designed. In addition to that, there is of course some heat generated. As we know, whenever two surfaces they rub against each other, heat is generated, and that heat has certain effect on the effectiveness of friction that we achieve. So again, those effects have been studied, and it is found that more or less satisfactory performance is achieved. The third apprehension about the sliding isolation system is what if there is some accumulation of dust or some foreign particles. So as you can see here, they are typically enclosed in some cylinder, and they are able to be protected from any external debris as such. However, they can be even inspected also. We can approach these bearings, we can reach to them and check out as to if there is some defect in there or not. In case we found some defect in there, during the functioning of the building itself, we can remove individual isolators whenever we so wish. If you note, the thickness of this isolator is extremely low as compared to the other conventional elastomeric bearings, and I will talk about that the plan size as well as the thickness of the sliding isolate systems are typically lesser, significantly lesser than the conventional elastomeric type of isolation system. So apart from these advantages of sliding isolation system, there are three additional advantages of the sliding isolation system which I would like to highlight. So first of it is the friction force that is developed at the isolation level. It is independent of the earthquake excitation frequency. And even the excitation frequencies contained within the earthquake ground motion. Even for the asymmetrical structures where the center of mass and center of resistance does not match otherwise, when we are using the sliding isolation system, particularly the one that we are seeing in the picture, there is a quite matching of the center of mass and center of resistance, and the frictional force that is developed in base is at the base of the building proportional to the mass of the building. Now what you will observe in one of the subsequent slides is what happens to the moment at the isolation level. But for the torsionally coupled system, it is advantageous that sliding systems are introduced so that the effect of the torsional coupling is minimized or almost nullified. So with that quick introduction about the sliding isolation system, I'm quickly moving on to the real life project where some advanced sliding base isolation system with double curvature have been used. So this project is now almost towards completion. So I will give systematically how the project developments happen. So this project was taken up by the Registoflex in association with IIT Delhi to use these kind of isolation systems and demonstrate the effectiveness as well as the technology to the Indian diaspora in the construction industry. So there were some of the objectives that we would like to meet. So of course, one of the objective was continuous functionality during and after the earthquake, that to major earthquake. Most of you have already read in the newspaper or even experienced, those who are in Delhi region. There have been frequent tremors this year. Almost 14 to 15 tremors we have felt. One last week itself, we have felt one earthquake. So Delhi lies in seismic zone 4, and thereby here the client wanted to make sure that this building is not only earthquake resistant, but also this commercial building should be uninterrupted in its activities during and after some major earthquake. Apart from that, not only the building should be safe, but the contents in the building and the occupants in the building, they should be protected. So that is the advantage of base isolation system as compared to any other response control devices such as the viscous or viscoelastic dampers or friction dampers or buckling resistant braces. Whenever base isolation is used in the building, the contents in the structure, they are protected. So this is a small animation that shows as to how a fixed base building and a base isolated building compare with each other. I would request you to note what happens to, let's say, this cabinet here, or these tables and chairs here, or the fan here, as well as what happens to these kind of roof tanks during the earthquake. Here you would notice that the isolation systems are introduced somewhere at this location. You will be able to compare between the effectiveness of the base isolation for protecting not only the main structure, but also the secondary structures or equipment. So these are those double concave or double curvature friction pendulum system that I will be now talking about, which has been used in this particular project. So this project consisted of a reinforced concrete structural frame. Again, I would still say it is a conventional one. The building site is located in Noida. It is in seismic zone 4 of India. And the requirement, as I have said, is the continuous functionality and to introduce the novel double curvature friction isolation system to protect not only the main structure, but also the contents within it. And the motive behind this structure was also to showcase the base isolation technology and the transfer some of the state-of-the-art research in base isolation to the Indian construction industry. Now, this objective was also important while deciding the location of the isolation system. So as you have seen in the previous animation, we could have put the isolators either at the basement floor, below the ground, or at the ground level. But because it is a showcase building, so we decided that let us put the isolators at a level that the visitors can be easily able to see. So that decision went in particularly for this building. I'm making this kind of a disclaimer that it is not always hard and fast that you put the isolators at 1 story above. It is again a decision of the designer as to at what level the isolation systems to be put. In this particular project, it was the decision related to the placement of the isolator was based on this requirement of exhibiting the technology to the visitors. This was the planning given by the architect, as to where the location of the columns are and how many columns in this building had been. And what you will notice here is there are some long span beams, which is in the order of 10 meters. And this is a columnless area in particular. Now, it was again our decision to decide as to what should be the location of the isolation system plan wise. So we decided that in this particular project, the isolation systems will be provided, the same isolation system will be provided at all the columns except the two diagonal columns where we have decided to have two different kinds of isolation system. So the height of the structure is around 26 meters, and this is a basement plus steel plus 5-story reinforced concrete building. The normal grade of concrete ranging from M25 to M30 were used in the construction of the foundation columns, beams and slabs. The reinforcement grade used was Fe500D. This building was analyzed a little in a different manner. Please note that this was designed few years back when the first draft of the Indian Standard Code on base isolation was yet to be released. So the building above the isolator level was analyzed and designed as a reinforced concrete ordinary moment resisting frame. The building below the isolator level was analyzed and designed as per the special moment resisting frame SMRF condition. This is a commercial building for use for commercial purposes, for the offices and other such purposes. So the importance factor had been 1. So obviously, if it would have been a hospital building, we would have taken a higher importance factor. So the response reduction factor, which is typically a debatable matter in case of especially the superstructure of base isolated structure. In this particular project, we decided to take the response reduction factor as 3 above the isolation level and 5 below the isolation level. Having said this, it is still recommended that the response reduction factor, particularly above the isolation system, can be in the range of 1 to 2. And the new isolation code in India will have some discussion on this part. If it is 1, then the superstructure would be mainly designed in the elastic range. And if it goes up to 2, then some non-linearity is expected. However, when we say either immediate occupancy and continuous functionality, in my opinion, the response reduction factor should not be applied, because whenever we say response reduction factor, it simply amounts to some damage, because we do allow cracking, and when we allow cracking, it is obviously damage, and that is something we may not welcome, particularly in the hospital buildings. Therefore, in my opinion, the hospital buildings may have their response reduction factor 1. It means no nonlinearity or no damage is allowed in the hospital building, so that even the plaster is not falling off or the cover concrete is not falling off on the patients. Anyway, otherwise the response reduction factors are applied up to about 2. In this project, we have applied it as 3. So without isolation, this structure had a time period of 0.44 seconds, whereas we had decided for the base isolation structure, the time period we achieved is 3.6. Thereby, we have achieved a time period enhancement or elongation of the time period by about 8.2 times. So as I have said in the beginning, even if we achieve time period lengthening by 3 or more, we start achieving beneficial effects of the base isolation system. So this is the sectional elevation of the showcase base isolated building. The highlighted portion, we have shown some details of that. You can see at the ground plus 1 level, we have shown the isolators. And then this is the lift core or lift well. So it is a kind of hanging lift well. It does not touch the ground here. There is a gap, and I will show you those details. And then some seismic gaps that we have provided in the staircase region immediately, after one enters the structure at the entrance lobby. And what are the other details in this part? What you would also notice from this is the sizes of the columns. So sizes of the columns below the isolation systems are relatively bulkier as compared to the sizes of the column above that. And again, it was a deliberate design decision that we had taken. And the advantage of these base isolation system incorporated in the structure was, of course, reducing down the design requirements or the demand on the superstructure above the isolation level. These are the locations of the isolator. As I have said, under every column we have provided the isolator, and the two diagonal isolators were of different kind and rest of them were of the similar nature. So at the isolation level, we have maintained some gap with the adjacent members, and that gap is around 275 millimeters. And whereas the lift core is hung, so there is a clear gap here from the bottom as well as on the sides. So the isolators are placed on a flared column having some pedestal here. Though again, we could have still accommodated it on the column itself by choosing appropriate size of both the columns and the isolator. But here, this was our decision to put it in this manner. One of the advantages of sliding isolation system is that this footprint of the isolation system is significantly reduced. And even within the sliding isolation system, the footprint means the planned dimension of the conventional single curvature friction isolation system is larger than the double curvature isolation system. In case of double curvature isolation system, the same effectiveness of isolation can be achieved with a smaller size isolation system when we see from the top. So these are the details at the level of putting the isolators. Again, you see here a kind of a column capital, both above the column as well as above the isolator. We could have still placed this beneath, immediately beneath the beams here. However, again, it was a design decision to put some larger size member at this level. This floor slab, of course, acted as a base raft or the base mass, which is essential for activation of the seismic isolation system. Again, there is a word of caution here. The thickness or the depth of the capital cannot be as large, particularly when its planned dimension is lesser, because then the effectiveness of isolation system will be reduced because the degree of freedom associated with the isolation will be shifted. So it is important that the degree of freedom of the base raft is as close as possible to the isolation. Thereby, the effectiveness of isolation can be better achieved. Now, in the absence of the codal provisions in India, when we taken up this project, we relied on some international codes and saw as to what practices they have adopted. So there are different procedures available, and today morning, Professor Deb has already explained the design procedures. So I'm not going to repeat those parts. Very quickly, there are static analysis, dynamic analysis, and equivalent lateral force procedure available in the different codes, particularly that from the US, ASE7, and that from the Japan. So out of that, equivalent lateral force procedure is pretty simpler and straightforward. It is kind of comparable with the seismic coefficient method. And for taller, relatively taller structures with higher nonlinearity, essentially most of the codes recommend conducting the nonlinear dynamic time history analysis or the nonlinear response spectrum analysis. So some of these details I will go forward quickly because already Professor Deb has covered them. In the response spectrum method, essentially we model the structure as first as a single degree of freedom system, and we incorporate the inelastic isolation system or nonlinear isolation system at the bottom and determine the response based on the available response spectrum. There is a practice of using the linear response spectrum in case for the nonlinear isolation system, we convert the force deformation loop into an equivalent stiffness and damping force deformation loop, and then still we can use the linear response spectrum. So for that equivalent linear system, for all practical purposes, we are able to obtain the results satisfactory enough for conducting the design. However, they have certain limitations. of this equivalent linearization. The advantages of the equivalent linearization of the force deformation curve is, of course, we can use the code-based design, or we can use the linear analysis and design of the base isolated structure. Whereas in case of time history analysis, we need not to do this kind of a linearization, as well as we can model the entire structure, including the different degrees of freedom. However, we need to have some time histories. So typically, we use the spectrum compatible earthquake time histories. They are compatible with a particular spectrum, maybe specified in a code, in a particular national code for a given soil condition and some site specific conditions. So when that scaling is done and when it is made spectrum compatible, we can conduct the nonlinear time history analysis. So this is a simple stick model for the multi-story building with the base isolation, which can be modeled in the conventional software that are typically used in structural engineering, such as ETABS or SAP, where the Bauquin type of models are already available in order to model even bidirectional response of the isolation system, which could be highly nonlinear. If you have a look at the building standard law in Japan, the structural calculations are required for multi-story building essentially. And whenever the height is more than 60 meters, time history analysis is mandatory and it must be reviewed by a special committee. However, for the heights lesser than 60 meters, response spectrum analysis can be conducted and some local government officials can check it. So in this project, we decided to conduct the nonlinear time history analysis as well. And we were involved in this modeling process of the highly nonlinear isolation system and its equivalent linearization. So what you see in this picture here is the isolation system that has been used in this project. It has two curvatures here. This is the upper curvature and this is the bottom curvature, same curvatures, which again helps us in reducing the size of the isolator, whereas the time period elongation can still be obtained. Depending on what is the friction, what is the curvature here, whether it is a variable curvature or whether it is a variable friction, the force deformation loop will significantly change. This is again a representative force deformation loop, not necessarily for this kind of isolation system. It can be a double concave or double curvature isolation system with variable curvature or with the variable friction. For example, in some project, it might be important to have the hardening effect after a particular design displacement is reached. So that hardening behavior can be obtained either by varying the curvature or by varying the friction in the isolation system. However, for all practical purposes, we can linearize this. The linearization is done by simply connecting these two peaks here, peak force and peak displacement in the first quadrant and peak force and peak displacement in the third quadrant. When they are connected, we get effective stiffness. And the area enclosed by this force deformation loop in one cycle is the amount of energy dissipation that is achieved, and that can be the damping of the system. So in this particular project, we have chosen two types of isolation system. This is the isolation system that is available at the site for any visitors to have a look closely. So the two types of isolation system had different stiffnesses and different coefficient of damping. So the isolation time period that we achieved in this structure is 3.6, as I said earlier, and the number of total isolators used are 15. So the behavior of this double curvature isolation system is shown representatively here. And of course, for this, we have used the equivalent linearization, and the effects of those equivalent linearizations are in detail highlighted in one of our earlier publication, which Professor Jangid had cursorily referred to, which has also received the Best Research Paper Award from IIT Bombay. So there we discussed about what if we have the equivalent linearization and what are its effects on the response of the structure. I was mentioning about the reduction in the torsional coupling in the structure. As you can see here, the two reactions are matching in the vertical direction, aligning with each other. And this is the reason why the torsional coupling in the sliding isolation system, the structure is lesser. What you see on the left is the model that was developed in the ETAP software. I'm again highlighting this because the structural designers who are in the audience today, they would note that uh, this is not a rocket science. This can be done in the conventional practice that we have been doing in structural engineering in India, where we can easily incorporate base isolation systems in our analysis and design. So this is the idealized force deformation loop. And then we have linearized that also by calculating the effective stiffness. But if we conduct some nonlinear time history analysis, of course, we do not get such a smooth and nice curve. So the effect of that linearization is clear, particularly on the isolation systems, and as well as what is the effect of the sliding isolation systems on the content of the structure, that is the secondary equipment in the structure, how they are protected vis-a-vis the counterpart isolation systems based on the elastomer. So what we see in these plots, which are based on the frequency, are the higher mode excitation is more in case of the friction isolation systems as compared to the elastomeric isolation systems. However, for all practical purposes, this may not be as detrimental, particularly if the equipment frequency does not match with some of these modal frequencies. But otherwise, the friction isolation systems are equally effective as compared to the conventional isolation system, if not better. So some time history analysis was conducted based on the spectrum compatible scale time histories. The spectrum was taken from the Indian Standard Code, modified for the seismic zone 4, and for the maximum credible earthquake, we saw as to what is the performance of these isolation systems. So this is the real isolation force deformation behavior in one direction that we have obtained by conducting the nonlinear dynamic time history analysis in the ETAP software. So once we design the isolation system and the superstructure corresponding to the forces that were reduced because of the incorporation of the sliding isolation system, of course, next part was what are the forces transmitted to the foundation. Obviously, the forces transmitted to the foundations reduced down because of the use of base isolation system. So foundation was modeled in the SAFE software, and the base raft was designed. So while giving the bearing capacity, we checked on the site as to what is the net set bearing capacity, and it was found to be around 35 ton per meter square. You can see that there is a lot of loose clay soil surrounding this, and this is clay sandy soil typically observed in the Trans Yamuna region. Therefore, because of the poor quality of the soil here, some treatment was given at the foundation level, and micropiling was done. Please note that this is not invariably required for any project. It is particular requirement of this site where the soil conditions were poor. So upon micropiling, raft was constructed, which was around 800 millimeter thick, a uniform raft. One may see that it is relatively thicker a raft because we wanted to ensure that there is no differential settlement that takes place, particularly when you have a loose soil underneath. It is important in case of base isolation structure that the differential settlement is avoided as much as possible. So after the substructure was constructed, means from the basement up to the first floor level, the next step was, of course, the installation of the bearings or isolation systems above all the columns and the column capitals. So we had several demonstrations given to the structural engineers from India, and otherwise we have also given training to the constructors. So these are the pictures taken on the site. First of all, we explain how does that isolation system look like and how it is put on the top of the column pedestal. What you again see here is the isolation system. You can get a feel of the scale, that how thin it is, and also you can see the protection against the any debris or any dust that can enter in. You can see mainly three parts of this isolation system. This is the top concave or curved surface. This is the bottom concave surface, and this is that articulated slider. This plate gets attached to the bottom in the column concrete, and this part, this plate get attached to the superstructure when you construct the columns above this. This connection is done through these connectors here, um, which are embedded inside this pedestal. Now, the alignment of this isolation system is a key here. So in order to ensure that these isolation systems are perfectly aligned and their layout is as per the design, the total station has been used, and using the precise laser technique, it was ensured that their alignments are perfect. So not only their placement and alignment, during the construction itself, there should not be any damage that would occur or misalignment that would happen in the isolator. So all care was taken. In this picture, what you see is how it is connected to the column here from the beneath, and how it will be connected to the column above here after the superstructure construction would begin. And currently you can see that it has been locked. Of course, when the structure is complete and built completely, then this locking will be removed, and isolation will be effective afterwards. So in order to ensure that the installation of the isolation system is properly aligned, such kind of templates were prepared, and after the templates were prepared, the isolation system was inserted, again by making use of the total station to make sure that their alignment is perfect. And then the grouting was done, and this is immediately after the grouting was done in the bottom column. Again, you can notice the protection provided here from debris to enter inside the isolator. So this is the bird's eye view during the installation of the isolation system on all these different columns. Please note here, these two diagonal isolators are different, as I have shown earlier, as compared to rest of the isolation system. So these two isolation systems were relatively larger and in plan as such, and that was for some specific purpose. The idea was that we have provided one kind of a fuse, as you can see this black part here, so that whenever there is excessively large displacement after the maximum credible earthquake, there is some protection against that. And that protection, as Mr. Vipul Ahuja was also discussing with me some time back, that protection should not cause further hamper to the design of the structure, or it should not lead to any catastrophe because of the impact at the isolation level. So the design of this fuse was such that it itself dissipates some amount of energy upon that heating takes place, and in that process it restricts the dislodgement of the whole system on top of the isolation system. So this over travel protection was used in these two diagonal isolation systems. So this is one of the diagonal isolation system placed diagonally, two isolation system for the over travel protection. This is after the constructing superstructure. How do that the isolation system with the fuse has been used. Please note again, this is again specifically designed for this particular project for the two isolation system in order to take care of the excessively large deformation beyond the maximum credible earthquake. So this is that corner bearing, as you can see in this picture. Then the construction progressed for the superstructure. Again, it is very noticeable that the column sizes above the isolation level are much smaller as compared to the column sizes below the isolation level. So isolation systems have been already put in place. Again, one of the participants has asked a question as to is it necessary to put the isolation system afterwards? So that's not the case. Isolation systems are typically put during the construction itself whenever we reach the construction up to the level of isolation systems. So in this, what is noticeable is the member sizes in the superstructures have reduced quite significantly. As you have seen in the previous picture, the column sizes are much lesser. Here you can see the beam sizes are also quite lesser. So again, today's participants in the morning session as well as in this session have asked a question, what is the cost effectiveness? So we have conducted that cost effectiveness study as to what is the reduction in the member sizes and the steel requirement in the superstructure. And we have compared that had this structure been built with the fixed base condition. So I will show that comparison once I reach up to there. But what I'm trying to highlight here is the thin member sizes that we have been able to achieve by incorporating the double pendulum isolation system in this project. Obviously, the superstructure should be completely isolated from the substructure below the bearing. So we had to provide gaps at different locations. Here you are seeing the gap maintained at the staircase flight. So you can see that this flight can be able to this flight will be able to move relative to the flight in this direction here. So this you can see the clear gap between the landing here without again compromising with the rise here. So this rise is more or less equal to this rise without any change there. You can see in from other view it looks although a regular staircase as such, and from external also you can see how does this building now look like. So at the lift core, you can see surrounding the lift core gap was maintained so that it doesn't interfere with the surrounding structure. There will be no impact during the design earthquake. And here in front of the lift core, when the lift will be used, obviously we will have to provide certain architectural features such that the users can use this lift without bothering about this gap. Please note that this lift core is hung from the top and it is isolated at the bottom. So maintaining this moat width or isolation gap is important to avoid any impact with the adjacent elements. Not only this, there are some other requirements particularly related to the supplies. So all the supplies which do cross the isolation layer, isolation level. So you can see this is the isolation layer or isolation level. Above the bearing is the superstructure, below bearing is substructure. So these piping systems, they are crossing this isolation layer. You can imagine that had these elements been stiff, they would not allow a smooth movement or free movement of the superstructure. So therefore, all these elements have been put flexible. This is a flexible pipe here. This is also some flexible arrangement done for the electric wire, and they can accommodate displacement at least to the tune of 300 millimeters in any direction. So again, these are some architectural requirements in base isolation projects, such that the base isolation remains effective and the superstructure can move relative to the base without any restriction. So similarly, the other supplies, the piping systems, they were provided with the flexible elements in them, as you can see in the white color here, and they can accommodate the displacement in the range of 300 millimeters. Then, as I have said, we have also conducted some cost effectiveness study. Though this is not a full-fledged cost effectiveness study for the entire project, we were interested to know as to what is the reduction in the material consumption. So for the material use, particularly for the superstructure in the base isolated building, because the demand reduces down drastically, we were curious to know how does that affect the overall cost of the project. So we assume the current cost of info steel as 50 per kg, concrete M25 concrete 3,800 rupees per meter cube, and the M30 grade of concrete 4,000 per meter cube. And first we conducted a comparison of cost between the fixed base building and the base isolated building. Please note, this is only the material cost. There is no labor cost or any other costs are incorporated, because this was more of an academic exercise just for us to get an idea as to get some ballpark figure as to what is the comparison between expenditure we make on the base isolated building and a fixed base building. What you would note is the cost incurred in building the beams, columns, and foundations reduced drastically in case of base isolated building vis-a-vis the fixed base building. Obviously, slab has no effect of base isolation as such, so therefore there was no change in the material cost of slab, and the isolation cost was additional in case of base isolated building. So for whatever material and their types we have used, we found that there is a increase in the cost in the order of 6% in this particular project. However, it is notable that this is without looking into the performance of the building. Obviously, a fixed base building cannot be compared with a base isolated building in terms of its effectiveness. So then that intrigued us, and we thought, let us have that comparison as well. So after having this comparison made of the material consumption in general and particularly the steel consumption, which we saw that steel has been reduced quite dramatically for the foundation columns and the beams. But when we compared with the fixed base building, which are designed for the giving the similar performance as that of the base isolated building. Of course, it cannot fully match the way the base isolated building will give the effectiveness. It is not possible for most cases, but still we tried. So we tried two things. One is, can we achieve the drift same as the fixed base, the drift in the fixed base building same as that in the base isolated building. Obviously, in order to reduce down the drift in the superstructure of the building, we need to enlarge the sizes of the lateral load resisting elements or the columns. So we increase those sizes so that we can reach up to the drift that we typically observe in the base isolated structure. So because of that, the cost escalation was about 25%. Then we try to see what if we reduce down the sizes of the columns in the fixed base building such that we get a similar time period in the range of base isolated building. Of course, we could not reach because then the design was becoming impractical. But we tried to elongate the time period as much as possible in the fixed base building just simply by reducing down the sizes of the column. So that did reduce some seismic forces though. However, the cost effectiveness of base isolation was still proven, particularly from the performance viewpoint. So base isolation remains unbeatable when it comes to the interstory drift and the floor acceleration. It is not possible to achieve the kind of drift and the floor acceleration we achieve in base isolation in the conventional fixed base building. So still this comparison we have conducted and put forth that for the improved performance, fixed base building will require 25% more than the base isolated structure, if not furthermore, and still the comparison may not be in terms of the performance. We also conducted in the FEMA framework the benefit cost analysis for the base isolated building, and we found that the benefit cost ratio for the base isolated building is in the range of about 2.5 in this project. So with this, I conclude my presentation today, where I wanted to take you through a real life project where the double concave friction pendulum isolation system has been used with articulated slider, with or without variable curvature and variable stiffness. So here we did not use the variable curvature as such. This has helped us in achieving a force displacement relation that we wanted to achieve with a certain restoring capabilities while ensuring the seismic energy dissipation. Here we were required to have smaller sizes in the plan for the isolation system because of the double curvature as compared to the single curvature, and even for the friction pendulum system, the sizes of the isolation system in plan were significantly less than the conventional elastomeric isolation system. In addition, the double curvature friction pendulum system gave us the advantage of not only the reduction in the superstructure forces, but also lowering down the torsional coupling effect, which are otherwise prominent in the asymmetrical structure. Because in this case, the center of mass and center of resistance, they were coinciding at the isolation level. And eventually we saw that the cost increase in this project was hardly about 6% in the material cost. As such, of course, one would argue that the flexible hoses that I have shown, that is yet another requirement, but I don't think it will increase the cost enormously. However, all this additional investment that even if we talk about, it is for achieving the significantly higher seismic performance to the tune that structure remains completely functional during the earthquake. And the persons who are using, the occupants of the building, base associated building who are using, they would not even feel the earthquake while the major earthquake happens here. So considering those significant advantages of base isolation systems, I think 6% cost additional in terms of the material is justifiable. So with this small note, I will conclude my presentation and will be glad to take up some question, whatever that you have. Thank you very much for your attention.
Uh, Thank you so much, Professor Mutsagar. It was a very illustrative and eye-opening presentation. I'm sure for the a lot of the most of the viewers, and they would take away a lot from here, and hopefully the whole idea of the base isolation will take on from here. Hopefully, I think, and it's demonstrated that the average consultant can easily take up this process and this technology quite easily after you've made it so easy. So, there are some few things that we had earlier discussed that you would like to deliberate upon a little bit. I think one is, what is the advantage of sliding mechanism over the elastomeric action? Okay. Additionally, in the context of safety of of occupants and equipment and secondary systems, the advantage is taken from others. So if you can talk a little
Yeah, so rather I would say the disadvantage of using the isolation system based on the sliding friction is that the higher mode response is amplified in case of friction isolation system as compared to the elastomeric system. So what you see in this plot is the Fourier amplitudes of the top floor acceleration. So this is the isolation mode here. So you can see that the isolation frequency has reduced down as compared to the fixed base. So for here, for the fixed base condition, the frequency is 2 hertz, whereas for the isolated case, it is 0.5 hertz. Now, because of that, the peak has reduced drastically. It means the acceleration has reduced. So in terms of reduction in the acceleration, both elastomeric isolation systems and friction isolation systems, they are almost comparable, where as compared to the fixed base building where the acceleration is quite significantly high. This is in the
both
first
are
mode.
equally effective. Both are equally.
Yes, both are equally effective in terms of achieving the response reduction in the acceleration. But this is in the first mode, sir. If we see the higher modes, here the higher modes are not amplified. So the FFT amplitudes in this frequency range, higher frequency range, is very low. In case of LRB, means conventional lead rubber bearing, laminated rubber bearing, and the lead rubber bearing. But in case of friction isolation system, you would notice here that the high frequency components are also excited. Now, if we have some secondary equipment that is sensitive to this frequency range, for example, there is some generator which has a frequency of 4 hertz. Now that frequency of 4 hertz of that generator is matching with this floor, the frequency of the floor or the acceleration FFT of the floor acceleration here. So there could be some amplification in that response for that secondary system. So this is the kind of disadvantage of the friction phenomenon. In terms of energy dissipation, seismic energy or input energy dissipation, these two are completely different phenomenon itself. The mechanism through which the energy dissipation takes place in the elastomeric bearings, and for that matter in the lead core, when the lead core or the lead plug is chopped off, the energy dissipation is completely different than what is in the friction. So here it is the sliding friction within which the energy is dissipated as against the deformations in the elastomeric bearings. So
Then can these isolators be fabricated in India, do you think? I mean, have you now come across people who are ready to build, to make isolators in India as per our new Atmanirbhar Bharat scheme launched by the government?
Sir, the very purpose that I frequently say that base isolation is really not a rocket science. We should still be able to utilize our own base isolation systems in India. So, though I have a strong feeling that these base isolation system, not only the sliding isolation system, but even the elastomeric isolation systems, we can definitely make them indigenously. However, because their use is limited, so commercially it may not be currently viable because expenditure, the initial expenditure, initial investment might be higher, and the customers may be a little less in number. So orders might be less. So because of this commercial aspect, it is it's kind of a chicken and egg situation, that because there are no locally available isolators, so there is a lesser tendency of adopting this in the real construction, and because there is no demand from the construction industry, probably no manufacturer is coming forward. So somewhere this cycle has to be broken. So if I compare the manufacturing technologies in terms of the factory requirements or the initial investment, again, this is still, I would say, a layman's comment that the manufacturing or fabrication of sliding isolation systems is easier relatively as compared to the elastomeric isolation system, as well as in terms of the initial investment required for these kind of plants. So to me, it appears that it is possible, or rather it is easily possible for the Indian industry to fabricate or to develop their own isolation system plants here in India, so that the cost part can be reduced down drastically. Again, I can give a ballpark figure that the cost can be brought down almost two-thirds, if not more, if we develop these isolation systems indigenously. Because otherwise, you can imagine transporting these heavy isolators from abroad overseas. That itself is a humongous cost that we have to incur. Whereas if they are locally made, as per this Made in India or Atmanirbhar initiatives of Government of India, definitely the cost will reduce down at least by two-thirds, if not more, sir.
And how about the relative economics between the the friction pendulum and the LRBs?
Okay, yeah, so it would be more or less in the similar range that I have projected here in this particular base isolated building showcase project. The escalation in the cost was somewhere in the range of 6%. So it would be more or less same if we achieve the time period that we have used in this case. So it is basically the function of the time period. So in case for the elastomeric bearings, we are achieving a time period of 3.6 seconds. Then the superstructure cost in terms of the material required for building the columns and beams will probably more or less remain exactly the same. There will be not any change. Only the cost of isolator would vary. So that depends on who the supplier is and where it is manufactured. But otherwise, the superstructure cost, material cost will remain the same if we have the same time period of the base isolated building. In case of
In
elastomeric,
terms of basic cost, the rubber bearing or the friction pendulum.
yeah, typically elastomeric bearings are relatively costlier than the sliding isolation systems. Yes.
So, but what hinders the adaptation of this technology, do you think?
I would still say it is the inertia between the minds of the stakeholders. Of course, one of the purpose of this particular building is to build the confidence in the Indian construction industry and the stakeholders.
So, despite like what happened in Bhuj, still base isolated technology is not essentially adopted even for hospital building. Probably Dwarka and hospital in Delhi and LD hospital in Srinagar.
Yes.
A few others only have adopted it.
Yeah, so after the during the Bhuj earthquake, the Bhuj hospital building has collapsed, and there were fatalities happened. And then it was quite sensitive a matter because the hospital is supposed to remain functional during the earthquake, and even post earthquake. There might be some increased inflow of the patients. but that hospital itself collapsed. And when it was rebuilt with the base isolation technology that to demonstrate that base isolation is essential for the lifeline structures or lifeline buildings such as the Bhuj hospital. That time there was significant talk amongst the developers and builders, particularly of the major hospital buildings, that it should be base isolated. However, later on, we are seeing that many major hospitals are still with the conventional earthquake resistant technology, excepting the Dwarka Hospital building here, which Mr. Mahinder Raj has been involved in designing, which is base isolated, and the hospital building which is coming up in Srinagar for the LD hospital. There are other hospital buildings in the northeast which are being built with the base isolation technology, and some in Bihar. But again, these are very few. Rest of the hospital buildings, mostly which are newly being built, they are with the conventional fixed base technology. So therefore, in my opinion, this is a high time for particularly those developers or those builders who are in the construction of the hospital buildings to adopt the base isolation technology, because of the advantages that I have mentioned, which are most relevant to the lifeline structure like that of the hospital buildings, to adopt the isolation technology in building the new hospital buildings, if not for retrofitting the other major hospital buildings in India.
Then I have a few two or three questions. Have you ever tried these memory shape alloys, like with the isolators, to restore, restore the original position of the building in the event like you have to choose a very flattish, friction pendulum? Has that ever been tried?
Yeah, yeah. This is. I mean, I am familiar with that, and we have done some work at IIT Delhi. But maybe if I may request Professor Jangir to respond, because one PhD research scholar who graduated with him, he used the shape memory alloy for increasing the restoring capability. Professor Jangir, if you would like to respond on this question, please.
We,
Yes. Hello.
yeah, yeah,
Hello.
yeah.
SMA is it's a supplementary device which is used along with the base isolation system. And this is again further used to dissipate the energy. That's the one purpose. And second, it the displacements.
Okay. So it has been tried, but it's still more experimental right now than in production.
It is in experimental stage. So what we can say that for this particular building, the gap was provided as 300 mm. Suppose someone wants to further reduce, make it 250 mm. So maybe SMA can be further be attached along with the FPS bearings. Put SMA, maybe your displacement requirement will come down to 250 or a 200 mm.
Or conversely, if you want to elongate the period for, let's say, a more flexible, and then you can want restoring forces.
It's a more like a energy dissipating device. SMA has a two state amount. One is the initial state, then it goes to another state when it changes its property amount. And through that we get a hysteresis loop amount. And through hysteretic we dissipate the energy. Like the purpose is very similar to the lead core which we use in elastomeric bearings.
Okay. Then
so SMA helps in that way.
Okay. Then for the substructure, Professor Matsagar, do you recommend that the same R equal to 4 or 5 should be used, or it should be more like R equal to 1 type, so that we don't get a ductile failure in the substructure? Otherwise, do you think that the period of the whole building will get affected?
Sir, this is a debatable matter, I must say. And in the core committee meetings also, this is being debated quite extensively. You were there with me during our visit to Japan, and there also we were discussing that when we say response reduction factor higher than 1, we simply mean that we are allowing some damage in the superstructure.
We don't.
Now, I would always wonder as to why we should allow that damage when all the seismic input energy can be dissipated at the isolation level in the isolator. So we have one particular element specifically designed to dissipate the earthquake input energy. Then why should we worry about the columns also to contribute in some energy dissipation? We need not to. It's
No,
my opinion.
I'm talking about the substructure, not the superstructure.
Sir, substructure we typically design rigid so that the acceleration can be transmitted almost as the ground acceleration is. If the substructure is designed flexibly, the effectiveness isolation reduces down.
So therefore, the substructure should also be designed for R equal to 1 or 2, something like that.
Yeah, so substructure typically we design for the lesser value of R so that there is no non-linearity. Non-linearity is introduced in the substructure.
Because
Typically,
you
it
demonstrated, I think, on the slide that the substructure were designed at R equal to 4 or 5, no, or 5 or something.
yeah. So in this case, this was a specific design. As I have said, here our design requirements were a little different. In general, as a design philosophy, the substructure is designed in such a manner that the accelerations are transmitted without as much as damage. Here, we were not much worried about that. Our purpose here to put the isolation system above three levels rather is because we wanted to showcase the isolators, but typically it is not a practice. The typical practice is that the substructure is almost, it is
Should
not
be
there.
elastic.
The isolators are immediately above the foundation, and thereby there is no question of response reduction factor. But
Well,
if I
actually, normally there are, for
for
most buildings, there are basements. Usually, at least 1, 2, 3 sometimes. So that's why I asked.
yes, so in case of the buildings with the basement, again, the designer decides the location of the isolation system. So in some of the base isolated building in Japan that we have visited, the isolation systems were installed beneath the basement floor itself. So the isolation systems were like one level or two levels below the ground level. So we can definitely install the isolation systems in the basement. So it is again the choice of the designer where to put the isolation
So
systems.
my
And in terms
question is
of design
basically
again,
only for R. The R value for
yes.
below the ISL interface. I'm not talking about where choices for the designers, but whatever structure is below the isolation plane should be elastic.
Yes, sir. So the philosophy that I am mentioning here is the seismic energy which is input to the structure can be dissipated at the isolator level by the isolator. Thereby, other structural element, be in the superstructure or substructure, should not be required to dissipate any energy. We have a specific element available in the structure for this purpose. It will be taking care of the seismic input energy. Then why should we worry about other members to contribute in energy dissipation? In my opinion, it should not.
May I ask a supplementary question to that? Professor Matsagar,
Yeah.
if that be so, what would be the comparison of displacement? Suppose you allow elastic deformation of the superstructure or do not allow. Will there be any difference in the displacement?
Sir, are you talking about the displacement at isolation level, you mean?
No, no, no. On the structure in terms
Yes,
of the
anyway,
performance.
because of incorporating base isolation, the drift reduces down drastically. Particularly in the first mode, the superstructure almost there are hardly any deformation. I'm hesitating to use the word rigid because it is actually incorrectly understood. So it's not rigid. It does deform. It does experience some deformations, means some lateral movement of the slabs relative to each other. However, they are extremely low. So the purpose of increasing the sizes of the columns in the superstructure is not required in case of the base isolated building, as it is required in case of the fixed base building if drift limiting the drift is the criteria for the design.
Okay, so one last question that I have is about the site period that you had in this showcase building. What was the site period?
Sorry, sir. What did
What
you?
was the site period? The period of the site itself, how much was
No,
it?
I have no idea. I did not look into that. We have used the
So,
soft soil, the category 3 of the soil condition for the response spectrum. We have chosen the third category,
okay,
but I don't think I have ever looked into the site period.
okay. Because
Yes.
does that play a major role in deciding
Yes.
the
Yes, you are right. Yes,
period?
because if you have soft soil, it's very clear that base isolation is less effective. In soft soils, when there is a significant amount of soil structure interaction, because the soil itself or the founding soil itself is flexible, so effectiveness of base isolation is less. Of course, if we still compare with the fixed base, we do get the effectiveness in terms of reduction in the seismic forces. But if we compare with the or the fixed base condition, the structure which is on the firm strata or rock, the effectiveness reduces down when you have the soft soil. Yes.
Okay, now I have
Vipul, I suggest you take few questions from the Q&A.
this is what
There are
I'm
a
doing
lot
right
many
now.
questions in the
Yes,
Q&A.
yes, I'm just
Yeah.
going, I'm now starting with that only. Okay, so can you explain, or I would say, this from Mr. Jitendra Rathore. Is it appropriate to mix various type of isolation systems in one structure?
Yes, very much. So we have been doing in almost invariably all the project where we are using the conventional isolation system. So typically the elastomeric isolation systems are put in those columns which are having higher reactions and which are typically at the corners, and in the rest of the beneath the rest of the columns we put the sliders. So sliders does not affect the isolation at all, so restoring is taken care by the elastomeric isolation system, and slider takes care of facilitating the sliding, means isolation is facilitated so that at the isolation level there is complete uninterrupted motion possible. This helps in economizing or rather reducing down the cost of the isolation system, because sliding isolation systems are much cheaper as compared to the elastomeric isolation systems.
But wouldn't the differential, vertical displacement become sort of a hamper in this case? For example,
Uh,
as an extreme case, I'll combine a slider with a, friction pendulum. In friction pendulum, the whole structure is rising, but in slider, it's not.
Yes, correct. So the sliders are designed in such a manner that the vertical direction play, I would say, vertical direction motion is taken care. So it has that kind of a, it can accommodate the vertical direction displacement to some extent. And again, that is a design feature of the sliders which are used in base isolation systems.
Then Dr. Dhawan says the life of the sliding bearings. What do you expect?
Hmm, I may not be able to comment on this. It depends on what type of material is used as the sliding surface. However, I would still say that these isolation systems are approachable. One can reach out to the isolation systems, see if they are proper, and they can be easily replaced if we found that there is some damage which has happened.
Okay, then Mr. Milind Gupta, which type of base isolation could be effective for long span steel roof, truss, frame, or subjected to vertical ground motion? If not, then which type of control systems would be effective for the same?
Yes, again, this question was, I think, also asked in the morning session. So Professor Dev has responded to that the similar concept can be applied in the vertical direction. There is also a concept of putting the isolators in 90-degree rotated manner. But for this particular case that he is asking, if we talk about a long span member, be it a truss or be it any member which is having the supports at farther distance, it is more affected because of the vertical component of the earthquake ground motion. So typically base isolation, if we are not using with that 90-degree tilted manner, then instead of base isolation systems, the vertical type of rocking viscous dampers are used. So this typically are prominent cases in the near fault location where vertical component is significantly high. So in New Zealand, we have seen such systems because it is almost on the lying on the fault. So there, for the rocking motion control, they are employing viscous dampers in the vertical direction using some cables. So they are put along the length of the member. So in this case as well, for the long span roof, those cables can be attached to the long span roof. Thereby, the vertical direction excitation or oscillations of that long span roof can be controlled.
Could some local mass also be added on to those long spans at a duration, let's say mid span or something, to change the frequency of the.
Yeah, only if it is a kind of a tune mass damper.
Right, exactly. So
Yes, yes, that is done. If we can put a tune mass dampers to control a particular response in a mode, maybe typically the first flexural mode, yes, it will definitely reduce down the response
and
time.
much cheaper just to put the masses over there.
Yes, it is.
Okay, so then yeah, so whenever we have to attack one frequency, then it will be a tuned mass damper type of an application.
Correct. Yes.
So kindly enlighten about the cost aspect of various size. I think it's already been taken care of. So, what are your suggestions? This is an anonymous saying. What are your suggestions whether or not we should use stiffness modifiers by reducing the gross moment of inertia, etc. So uh, for the superstructure and all. So, what do you think about that?
Yes, I think otherwise we call the superstructure design as aseismic. So ahead of seismic, we attach this letter A. So the superstructure, excuse me, superstructure design is aseismic. It means for any other load combinations of dead load, live load, whatever conventional designs that we are doing by, let us say, using Indian Standard Code IS 456, the similar procedure
So
needs to
what
be
they are
applied.
saying is, see that if you have the modifier, these reads on, if you use them, the modifier, the fixed base time period goes up to twice the value than without the modifiers. So, should you, so what do you suggest that should it be modeled as cracked or uncracked? Because, if you are essentially going to make it elastic, then it's more close to uncracked, more like a service modifier, service level modifiers than for the ultimate space. That's just all
Yeah,
that.
so I will restate. In my opinion, the superstructure should be designed without cracks
Right. So
in
then
case of a sensitive building.
so
But
for the service level, like for the service level earthquake, it's a very like a 10% crack or 10% reduction type modification. Okay, you can you use the R factor in the new draft code is anyway limited to 2.
yes,
Okay. So then we have Mr. Milin Gupta again. We for vertical ground motion IS 1893 suggested to take two-thirds of horizontal listing. Also from past studies, it has been observed that the near fault structure damage due to the vertical ground motion. Therefore, to improve the performance of long span steel roof, I think there's the same question.
yeah.
So then how to inspect the isolation device and replace, since it's placed at the bottom and for the future replacement is required, no possibilities of lifting the device to go underneath.
Yeah, so you would have noticed in my slides that the column capital is little larger in the size as compared to the plan size of the isolator. So those corners are used to put the jacks, and then the jacks they lift in that part the structure. We can remove the isolator and put the new isolator in there. So these replacements have been demonstrated not here in our project currently, but they have been demonstrated quite widely. If I'm not wrong, Professor S.K. Dev has also replaced his elastomeric bearings in the demo structure of BRNS in IIT Guwahati campus. Professor Dev, if you can throw some light on that.
Yeah, we have done that in 2007. Actually, originally it was built on uh, lead rubber bearing. Then we replaced it by high damping rubber bearing. Okay, It was a Herculean task because it was a slender structure, aspect ratio around 3. But we could do it. I mean, we tuned all the jack together so that the entire building, we lifted. Of
Yeah.
course, this is a small building. We could do it. Yeah, but then all the jacks were in phase, so we made that arrangement so that all jacks move up in the same rate and upward direction. And it was a task. Definitely, that was an experience for me. But we could do it. It is still
Well,
there, new.
yeah, I think the important thing is that the jacks should not be engaged the local floor beam. They should be under
Yeah.
the capital. If you engage the floor beam, then it will just shear off for the entire weight of the.
No, no. One has to design those schemes beforehand.
Yes,
We
yeah,
have
and people
designed
are,
those location where jack will be placed. Unless
yeah,
until we do that, it will break. Na shear
yes,
failure will
absolutely.
be
So,
there.
so
So
a lot
that
of
has to
people.
be designed a priori. A priori.
Right.
How you
So the
will
thing
change
is,
the.
these are code issues also that one needs to put in the codes. Because of faulty bearings or something happens later on discovered. Because a lot of people don't want to, because it's an extra expense, to have large capitals and stuff like that. So a lot of people are reluctant to even do that. So that's something.
It don't require, I mean, large capital. There will be two basement beam. So basement beam close to the support, you will have to design for shear,
For the whole weight
and
of the
that load
column
what
coming
you
on the
expect.
column, for the whole
Yeah,
dead load on the column.
we will not place in the column. There are two. I have shown. And this slide is not there with me.
Okay.
Two basement beam, one lower basement beam attached with the substructure, one with the superstructure. So in between that, we can place our jack. From 3 direction and 4 direction, you can take out the bearing. So that is
So
what we have done.
basically,
Uh,
replacement of the isolation bearing is a part of the design strategy. It has to be.
design strategy. Yeah, yeah.
It is
It
it
has
is
to be.
recommended. It
In
is
bridge you
recommended.
do na. In
It
bridge
is
we
recommended.
replace this.
Okay, but when people talk about 130-year life, that's the kind of it depends on the aging test that you probably do on the materials, either whether it's friction or the rubber. You know. So anyway, how to inspect the isolate? How to inspect the isolated replace. Then for showcase building, two different structures FE models were developed for the above and below isolator. How combined response formulated?
Yeah, actually, it was modeled as one
Sandeep,
structure only. It was not differently modeled.
so what's the code for design of isolation system in India in present? Anonymous.
Currently, the base isolation code in India is in draft stage, not even draft stage. It is being discussed. It has taken its shape. So maybe in next few meetings of CED 39, it will be discussed and approved, and then sent for the wide circulation.
For heavy, Sandeep, for heavy structure like nuclear vault, is there any possibility of failure of bearing materials? In such cases, can the failure system be repaired, replaced? I think replacement and all strategies we already talked about. Heavy means how heavy we should define. What is the, I think maximum testing machines are up to 7,500 tons in UC San Diego. So depends on how much, what is heavy, you have to tell us. So what is the life of the isolation system? Again, the same thing. How are they to experimentally find the coefficient of friction of the friction pendulum as it depends on the velocity, pressure, and temperature. How to choose a coefficient of friction at high velocity of sliding for practical design of FPS. And this is by Bennett.
Yeah, so typically in the practical designs, we do not much worry about the temperature or the velocity dependence as such, because the velocities that we are talking about in case of seismic excitations are much lower. So that marginal difference in the friction that we get because of the change in the velocity, it is ignorable. So we conduct the quasi-static testing. Professor Jangid has shown in a laboratory setup how he had calculated the friction coefficient. So similar tests are conducted in the industries where these isolation systems are manufactured, of course with some sophistication. But typically we do not worry about the rise in the temperature or the velocity dependence. Having said this, it's not that it cannot be done. It can be done, and we need to have that kind of testing facility for this prototype isolation systems. But as of now, as you have rightly said, Mr. Ahuja, dynamic testing of the isolator is possible for the prototype isolation systems probably only in San Diego facility, nowhere else, to best of my information.
So can we use a base isolation system with high-rise building having shear wall system as lateral load resisting system where the wall length varies from 2 to 5 meter length, Mohit Kohli?
So essentially it depends on the dynamic properties of the structure. If already the structure is flexible enough that it is not attracting significant seismic shear forces, then we need not to worry about incorporating base isolation in there. But if the frequency or time period of the building is such that even with the availability of these kind of shear walls, if it is attracting more seismic base shear because of the higher spectral acceleration, then there is a point in incorporating base isolation. So essentially it has to do with the time period lengthening or shifting of the time period from the predominant frequency content of the earthquake excitation to those frequencies which are not governed because of the earthquake excitations. So as I have said during my presentation also, if you are able to achieve a period elongation of 3 or more, I think it is advisable to go for base isolation.
Well, actually, also it will affect the acceleration, at the higher stories and all.
Yes,
So that's
definitely.
also an important benefit of the base isolation.
Right, sir. Right.
Okay. So, how the base isolation system differ from other than the vertical isolation systems? Does this vertical isolation system isolation is the same as isolation between the adjacent buildings? Does this vertical seismic isolation is same as the isolation between adjacent buildings?
Yeah, it is easier to imagine, sir. In the vertical direction, let us say the elastomeric bearings, one has to just rotate it in 90 degrees, and then it can take care of the relative displacement between the up and down motion of the structure. However, probably the question is also related to, in that case, what will happen in the transverse direction. It might interfere the lateral displacement of the structure. So naturally, we have to take care that the lateral displacements are not affected or they are not obstructed because of the vertical isolation. So these two systems, they are put together in terms of their functioning. And there are some publications by Professor James Scaly on combined vertical and horizontal isolation. So they can refer
Well,
to those.
conceivably, like if you have springs for the vertical direction and you
Yeah,
have
that is, yes,
springs for the
that,
lateral direction as well. So I think this may be more along those terms. So how does this affect the vertical isolation is the same as the isolation between the adjacent building. So, I think they're probably trying to say this is by Neha Rajput. So maybe she's trying to say that, if it rocks, so to say, so will it impact the adjacent building or something? So sufficient gap has to be kept because of the
yeah.
rocking if you have vertical isolation as well.
Yeah, so
Because of that
maintaining
rocking
sufficient
motion.
gap will help us in avoiding the pounding effect, seismic pounding.
Yeah.
And in case of if there is a chance of rocking, particularly for the slender building, having lesser plan size and height relatively more, then the rocking restraints are provided. Those rocking restraints do not hamper the isolation effectiveness because in the horizontal direction they do allow the motion, but in the vertical direction beyond a certain limit they do not allow the vertical direction motion. So thereby overturning is not allowed there. So slotted bolted type of connections are provided. So there is a special design which is made at the isolation level in order to prevent any overturning of the system in the vertical direction. But that is not response control.
So then there is this by Shilpi Srivastava. In case of lead rubber bearings used as seismic isolators, has it to be changed after a major earthquake and the lead will be yielded with a major seismic action?
No, the reason why we essentially use the lead there is that we are not required to change it after any major earthquake, because once the earthquake is over, there is a process which is called recrystallization. So because of the recrystallization of the lead column again becomes a uniform lead column, though of course in some deformed shape, but it is still available for the subsequent earthquakes to take and dissipate the energy. So it recrystallizes, it means it almost becomes one single lead column once again.
Then
Over
Mr.
a period of time.
Jitendra Rathore, 6% was the cost increase for the showcase project. What is the opinion that about cost impact of adopting the base isolation in case of large scale projects, whether it will increase or decrease?
Yeah, so there could be a possibility of even decrease in the cost of the base isolated structure as compared to the fixed base. That possibility still does exist, but that cost comparison has to be done maybe at the design stage in order to see how much is the escalation. But having said this, my ballpark figure is always base isolated structures are never more than 10% of their fixed base counterpart. 10% is the kind of upper limit of the escalation.
And that too, if they are made in India, sometime in the near future, it will be even better than that.
Yes, yes,
Maybe
definitely. Yes.
hopefully someday.
It might be cost effective as well.
Yeah, right, right. So I mean, that will be the biggest seller, I think.
Yes.
So then, Miren Gupta, for vertical ground motion, the IS 1893 Part 1 2016 suggested to take 2/3 of the horizontal ground motion. Also, from past studies, it has been observed that the near fault structure damaged due to vertical ground motion. Therefore, to improve the performance of long span steel roofs, I think this is the same thing, which type of size we already talked about this. Okay, so then code for design, we already talked about this. Then if after some years if you want to change isolator, the same thing. How about bearing is installed in a fully steel structure? Steel, how this bearing is to be installed in a fully steel structure. So I think
Yeah,
of
there is
detailing.
hardly any difference if it is a steel structure or reinforced concrete structure. Yeah.
So do we need to partial? Uh, do we need to use partial safety factor for earthquake load when it is considered in the linear or non-linear time history analysis?
Yeah, they are always there because we typically follow the limit state design philosophy. So they are always there.
Okay, please provide the YouTube link. Okay, which type of uh, bearing gives best results with economy? Well, I think we already addressed that.
Yeah.
I think then in the chat box, it's appropriate to mix the lateral design. Which type of base isolation would effective? And this long span already talked about. Then kindly enlighten about the cost aspect of various base isolation systems. I think we already talked about the various this LRB and friction pendulum. What is your suggestion whether we should not to use a stiffness modifier? I think we already talked about that. And there's a lot of duplications there. 2/3 pick the isolation device and also replace the showcase building, 2 different final models, the code. I think all these questions have been what is the life of the isolation system? This thing already talked about that. About base isolation system differ vertical seismic isolation system. Does this vertical seismic isolation is the same as the isolation between the adjacent buildings, the same thing? Case of, can isolation be used for masonry structures? I think this was already talked about in the morning.
Yeah, it can be used for masonry structures, though the type of isolation system look like, it doesn't look like that it is used for the columns as such. It is a continuous isolation systems. But the answer to this question is yes, it can be used for masonry structures as well, load bearing structures.
Uh, in, uh, can we use isolators in sloped buildings?
Yes, we can use the isolation systems when there are buildings built on the slopes, or even the foundations are at different level. We have to decide the isolation plane. The isolation plane may not be exactly kind of horizontal, so we need to decide as to how the displacement will take place, and it is not obstructed by the offsets that we have in the structure. That is one
I
possibility.
think,
Some other
go ahead, please.
Yes, please go ahead, sir.
No, what I was saying was, I think the substructure is should never be ignored. It's equally important, and that also needs to be symmetrical. So both in stiffness and mass. So if it's on a hillside or something, for example, and one column is very short and the other side column is very long, then we have an eccentricity in the substructure also.
Yes, correct.
That's one thing. And then, of course, if it's a sloping roof, for example, or something, then also one wall will probably be short as compared to the other wall. So that will be a eccentricity of stiffness, in the superstructure also. So as long as it is within limits and all, and it's accounted for, I think that should be all right.
Yes, sure.
Um, Ductile detailing of base isolated structures. Really information. If there is dB, will friction pendulum bearing come back to its original position?
Yes, that's what it is designed for.
Um, then base isolated structure should be made rigid. Please confirm. Only a small energy goes into the structure if we can, if we have a well-designed system of isolation.
Yes, sir. My answer to this question is yes.
Ductile detailing in base isolated structure not necessarily. Please confirm. I think we already talked about this. Which method is used for swinging for swing of friction pendulum? How is it designed? Okay, I think the interface material is what they're talking about. Yeah, at the friction pendulum.
Yeah, so earlier it was some coated steel, but nowadays they are using some commercially available materials which gives
I think they use PTFE as well as some proprietary.
PTFE was again somewhere in between. PTFE was used, but then some experiments were conducted, if I recall correctly, in Australia, and they found that PTFE experiences wear and tear during the number of cycles. So some new materials which are mostly patented, and those technologies I'm not familiar with, they are used so that wear and tear doesn't happen, and the friction coefficient is maintained with number of cycles, large number of cycles.
So, but response reduction factor also affected by factors other than the plastic difference. So it can be more than one. Question. Can it be more than one? Well, I think we already discussed a lot of this thing, and it's also under draft right now. So let's see. Why the base slab, base slab is necessary to activate the isolation. Can't it
Yes.
can't be provided isolators of the bottom of column without floor RCC slab?
No.
Dr. Moha.
No, otherwise the isolation system will not be effective. So basically you need a mass corresponding to the isolation degree of freedom. Then only the isolation system will activate. Otherwise isolation system will be idle without a mass associated with it.
A lot of compliments are there. Can we get a PPT on this? Excellent presentation. Please share your YouTube. Why base lab is necessary? Again, the same question. Very for vertical ground motion is, and I think we already discussed this part. And Mrs. Amuta for engineering and design, why wing of L&T construction? I am lead consultant for analysis and design of seismically isolated building using triple friction pendulum isolators in construction of cancer center building at 18 care hospitals in Assam at 18 locations. So I guess this probably is in response to our grouse that we don't have enough hospitals being built. So they're
Yeah,
seeing
but I have mentioned already
18.
that in the Northeast, there is one project coming up with base isolation system for hospital building.
So then comment, besides better performance, the life of FPS is nearly double that of LRB. Shirati Jain is saying. DST has funded a project on this earlier for your information, Dr. Uh, by Professor K. Kamal. And then there's great presentation. Friction pendulum is implemented in Assam hospitals. Again, the same thing. But for vertical ground motion, I think we already gone through this. The case of lead rubber bearing used for seismic isolator has it been changed after a major earthquake as lead will yield. We already talked about the draft code for base isolating circulation. Please send YouTube link. Can we use this isolation? There's already, I think, this YouTube link has been posted by someone. Friction properties of isolators are provided by the isolator supplier, which needs to be validated with the prototype tests. Okay, can we incorporate these isolators in uneven ground surface like building resting on slopy surfaces? Already discussed that, dear sir. The sliding isolators, it is always necessary to provide the structure back to its original position, even if it is possible to install base isolation devices in existing structure. So I think the first thing was the back. That's the restoring forces and recentering. We've discussed that quite a bit in the seminar, and then also it is possible to install base isolation system in an existing structure. I think there has been a lot of studies around or a lot of cases around the world. They have there's a retrofitting case.
Yes.
So of course, it's very tricky, but it can be done and could be done for, I think, mostly heritage building type things that you absolutely don't want to dispense with. It's not cheap. So production of SIPs is now taking place in India as well as prototypes produced already
Yes.
evaluated as well. Results are found in comparable range as that are produced in the US and Europe. From Jitendra Rathore. How would isolators be placed in case if the structure contains only shear walls? If a structure has only shear walls, how would you place the isolators?
Yeah, that also we have discussed that it depends on the dynamic properties. If we are able to achieve the time period shifting, then the isolation is effective. So it is irrespective of whether the shear walls are present or not present. And if it is related to retrofitting in the existing structure.
No, not retrofitting. Now there's a different question about if it's a shear wall structure, can the isolators be put in?
The answer is yes. Whatever the generic presentation that I have made, you need to adopt some certain different strategy for the case specific conditions where the shear wall is also isolated. Of course, shear wall will be used for the superstructure as such to ensure its rigid behavior. However, saying this, I think for the base isolated structure for from earthquake viewpoint, shear wall may not be necessary. So that shear wall will ensure that the superstructure is behaving more rigidly comparatively without as compared to the when there is no shear wall. But as such, yes, shear wall can be provided in a superstructure of base isolated building. I don't see any reason why it can't.
Well, actually, normally there's a transfer raft, transfer which below which there'll be columns for the basement. So the whole tower sits on that thick raft, and you'll have various columns below that. So how okay, performance of in fire, Mr. K. Ganguly.
Yeah, so these isolators are tested in the fire conditions. So there are some tests conducted on the prototype isolators, particularly the elastomeric bearings. Some samples go through the fire testing as well. And then there is one layer of elastomer which is put only for the fire protection on the isolation systems, elastomeric isolation systems.
Okay, any maintenance is required periodically for the base isolation devices?
Not as such, but seeing them periodically is advisable.
Okay, I think we have gone through all the Q&A, over, I think, 50, 60 questions. So that was very nice of you to be very patient with us and go through each and every question so thoroughly, Professor Matsagar. We really appreciate that, your lecture and in trying to propagate this technology, which is beneficial for the country as well as, in terms of better performance post earthquake and continued functionality and to improve the resilience of the society as such. So I think that it's a very important, not only for the, and this is resilience of either buildings, bridges, or any other kind of structure, lifeline structures, everything. Like Japan these days, it goes without even asking that residential buildings are also being, base isolated. So people, and there's a lot of premium on those because people know that they will not be disturbed after the earthquakes are so frequent. They don't want to be disturbed every time there's an earthquake. It's just that, we haven't had a Bhuj-like tremor since 20 years, but, it's, the writing is on the wall. So I think, uh, it's very important that, we adopt this and also any other of the technologies like dampers and, other tune mass dampers, whatever it takes, to improve the resilience. And, we don't want a situation like a pandemic, where the economy shatters for, over a year and for any disaster. So this is, in fact, a lot of research has been done, trying to draw parallels between, earthquake disaster and a pandemic disaster in terms of the resilience of the society to cope with it. So, and these are the nuts and bolts which will help in improving resilience. So thank you very much. So I hand it over to Mr. Alok Bhumik to take it on.
Thank you, Vipul, and I profusely thank both Professor Vasant Matsagar and Professor Jangid for such an excellent presentation. Very informative, very educative, and really thanks to share your knowledge and your research on this subject. And this is such a subject, this is a new trend in earthquake resistant design of structures. And you see, one advantage of base isolation or supplementary using supplementary device damping system in the structure is that you change the performance criteria altogether from a collapse prevention to maybe operational or immediate occupancy. And this is something which you are able to achieve without increase in cost. Rather, there is a reduction in the cost. This is something which I think is phenomenal, and there is very wide application of this in future, though we cannot sort of do it jump over in a short period. It will take its own time, and we should give time, because the technology is something which we have to adapt. Our industry has to gear up, our practicing engineers needs to understand. So this is a subject of the day, and I really thank all the four speakers today. And I would rather take this opportunity to request both Professor Matsagar and Vipul that why not we come out with a issue, one issue of our ACD, IS30, or even for that matter ISET journal dedicated to this vibration control, supplementary damping device, and base isolation. I think that will be a very good document which will help the practicing engineers to sort of use it, because in times to come we will see more use of this technology. Thank you all, and I think our next webinar is not going to be this year, it will be in 2021. So I use this opportunity to say Merry Christmas and Happy New Year to all the participants. Thank you very much.
Thank you. Thank you. Merry
Thank
Christmas.
Thank
you.
you.
Thank you. Thank you, Mr. Bhomik and others.
Yeah,